start recording. So lots of mistakes I made last time. So lots of mistake. So where was the mistake about the? Yeah. So the correction from last time. So last time, so we talked about the D1D. D1 D5 system, Q1, Q5, D5, and then as far as I remember, something like this one, and 1, 2, 3, 4, 5. Yeah. And this is T4, and this is S1. And then you have character line mode for. So this is the previous setup, and from here, once you take, so GS QI goes to like a 1, and then you get the supergravity, 5D supergravity description, and then here to take GS QI is less than 1, you get the 2D, and also 2D SCFD. So this is a description we'll have, and then yeah. So the last time, so first thing I made is that so I made a mistake is that the unfortunately I didn't print out this one. Yeah. Here also here, so this GSQP is 1 and GQ square. That's what I first remember. Yeah. QP GS square QP less than 1 is, so this is a correct, and this is 4,4. Sorry, this is 4,4, and yeah. So here, so you need to take also the limit QP is greater than QI. So I runs for 1 to 5, 1 and 5, of course, and the Q1 times Q5 for supergravity, 5D supergravity and limit. So this is the limit you want. Sorry, I made no. Yeah, no, sorry. So this is a limit you have to take, and which means this is almost GS is almost 0, almost 0. So almost 0. And 2D CFD lives on this direction. Yeah, 2D CFD lives on this direction, and T4 is very small enough. And R symmetry, so I told you wrong. So R symmetry, I should have known. I'm sorry. I don't know why. I mean, is SO4 cross SO4, indeed. So actually, supercharge of the 2D QQ bar for this one for dot is indeed Majorana while. So it's real. So it's real, and the form is for Majorana while supercharges. So which means real full supercharges come from holomorphic sector, and then from anti-holomorphic sector you have a full supercharge. And SO4 cross SO4 is the R symmetry. So the last time I told you wrong, SU2 cross SU2. This is not true. Sorry, this is not true. And SO4 cross SO4 R symmetry can be seen the symmetry of SO4 here and the symmetry of SO4. Okay, so I call it parallel. As far as I remember, I call this one is parallel and also as far as I remember. Yeah. So this is the correct R symmetry. So the geometry knows about R symmetry. So this is a mistake I made. And then also the mistake is, another mistake is that the, yeah, I made a lot of mistakes, sorry. Yeah, so the central charge of this 2D CFT is indeed a number of boson and then half of number of fermion, and which is 6 times Q1, Q5. Okay. Which come from, I told you the 4 come from here. So this is, okay, let me write down 4 times Q1, Q5 plus 2 times Q1, Q5. Okay. So where are they? So as far as okay, so this is a bunch of Q5 D5 brane, and then bunch of D1 brane, and Q1 D1 brane, and then so the bosonic freedom really come from this freedom that connect the open string that connect D1 and D5. So we call it D1,5 brane. Okay, and then so this 4, the last time I come from the diffraction normal direction. This is not true. It's not true. So this 4 really come from 4 direction of the torus. So open string can move around this four-dimensional torus on the D5 brane. So this is the degrees of freedom, bosonic freedom come from. And since it's supersymmetric, number of boson to fermions the same, then you have a multiply 1/2. So therefore, factor 4 really come from the freedom of the 1,5 brane, and that moves around the T4 direction. So that's the mistake I made. Last time I told you this is the fractation normal direction. This is not true. And then, so the partition function we look at is indeed 1 minus QM, 1 plus QM, 1 minus QM, and the 4 bosonic, 4 fermionic, infinity. So this is a partition function we look at, and we just take the expansion, which is number of mode of QP to the Q to n. Okay? So n runs for 0 to infinity. So here, this omega encounters the degeneracy at the level n. Okay? Level n. And this, again, 4 really come from the degrees of freedom of the this 1/5 open string can move around on T4 direction. So therefore, this 4 really come from this T4 direction. So again, last time I told you this is fluctuation around the normal direction. So I'm just showing the lack of my understanding of the string theory. Sorry, even though I teach string theory. Okay. So then we take Cardi limit, which is a homework. I highly recommend you to do that. This is the Cardi limit. And we get exponential 2 pi. 2 pi. This is homework. Q1, Q5, QP. So that's what we obtain. So here, Cardi limit is strictly speaking. So this is Q1, Q5 is fixed, but you take QP is large. So this is indeed Cardi limit. Sorry. So central charge is larger. Is fixed. So as I mentioned, central charge is proportional Q1 to Q5. So central charge is fixed, but you take the momentum, quasi-line momentum to be large. So this is a Cardet limit, so that the you obtain. So this Cardet limit can be obtained by S transformation. So maybe some of you guys already start solving homework. So this Cardet limit can be obtained by S transformation of this. So it's related to the modularity of this one. Yeah. So this is torus partition function, and tau can be understood the how to say 1 over temperature. 1 over temperature, is it correct? Yeah, 1 over temp. I mean the length of the tau 2, I would say, is 1 over temperature, and if you take the tau goes to very small enough, it becomes high temperature. It does exactly how the original study. So once you go from tau goes to minus 1 over tau, you get the high temperature limit, so that you can look at the behavior of high temperature, and so that that is really what Cardi original study. So you have to use S transformation to look at the behavior at around this region, and we saw that therefore, yeah, I mean, this is omega, so omega is so therefore, indeed, what we observe is log of omega is indeed the entropy of black hole. So left-hand side is computed by supergravity theory by taking this limit. On the other hand, so right-hand side, this is supergravity. And on the other hand, this microscopic counting is the d2d CFT. So this is the first done by Strominger-Baffa. In the case of, so they study in the case of T4 is replaced by K3. So as I mentioned, K3 is blow up of T4 on T2. So if you originally Strominger-Baffa studied the case of K3. So this system was studied by Karl Magnussen first. Okay, so the mistake I made is indeed this origin of 4 and the R symmetry and the Cardet limit. I just mentioned that it's just take large charge limit, but you have to be careful. So the central charge is fixed and the QP quasi-Coulomb momentum is taken to be large. That's the Cardet limit. Okay, so this is the correction from the last lecture. Now, so this is around 96, and then next year, yeah, there's a lot of work by, around that time, there are lots of work by Strominger and Marcena. And then late 97, he has proposed the so-called the famous CFT correspondence, which I'm going to talk about. CFT correspondence. So as I mentioned, so here, so when you take some limit, large charge limit, so here GS is still small but finite. In order to have the supergravity description valid. So that the QI and the QP takes to be very large. Okay. Here, whereas here GS is almost 0. Okay, almost 0, and the QI is some finite value, but the QP take to be large. Okay. So then here you have a theory of gravity. As you know, gravity is described by closed string. Whereas here, we clearly look at the open string, the theory of open string. So this one, another way to look at is this is closed open duality. So one side you have an open string description, the other side you have a closed string description. And in particular, today we are going to look at the famous example. So there are lots of example in the CFT correspondence. The most maybe famous one is ADS5, CFT2, CFT4. Sorry. Usually it becomes D plus 1 is holography. So D. So therefore, so sometimes it's called bulk and boundary. So which I'm going to explain today, so that it's called some kind of holography, which means that the D plus 1 gravitational theory is described by the boundary, one-dimensional, less quantum field. That's called holography. So which I'm going to describe today. Okay, so before then, so we study 2D CFT extensively, lots of OPTV computation and so on. So since we just look particularly focus on these 4 cases, so we just need to introduce what the conformal field theory in general dimension. So, so let's first talk about the conformal field theory in general dimension. So what are the So again, conformal CFT to CFT of general dimension is the QFT invariant under conformal transformation. Under conformal transformation, which actually G mu nu is again the same thing. Is under the conformal transformation, the metric is actually invariant up to scaling. So again, so D-dimensional manifold to the some diffeomorphism, and D is 1, D, 1, D minus 1 is mapped to M 1, D minus 1 as a diffeomorphism F, and the Pullback metric, and it's both considered to be Riemannian manifold. So if you pull back the metric from by diffeomorphism F, G prime is just related to G up to some scaling factor. So that's conformal transformation, and the CFT is so this is G prime. So then, so if you take the infinitesimal version of this transformation, what you get is again it's the same as the 2D CFT, but the correction there is equal to 2 over D pressure. This is the infinitesimal version of the conformal transformation. So the conformal transformation should obey this relation. And then once you take D equal to 2, that's exactly what I have seen, what we have seen before. Okay. Um, then you can again apply the define the apply pressure mu on this one. Then this equation will lead you to 1 minus 2 minus t. It's very simple manipulation. One can do is Laplacian plus. Okay. So that's easy to see. Partial mu acts. So you get the Laplacian, you get the del dot E, and then del dot then derivative. So this is exactly what you get, and something very special happened. So from here, d equal to 2. So this term vanished, so that the conformal transformation should satisfy this harmonistic condition. So this is the Laplacian in 2D. So this will give you the condition for E has to be holomorphic in 2 dimension. Okay. So in some sense, this can be understood as like this way. So therefore, E has to be either holomorphic or anti-holomorphic. Okay. So general D, so you have this term. So that makes a bit different. And you can further apply del nu of this relation, and then you will get the following: d minus 1 that's also easy to see. So I mean, you can easily see that. So if you apply now del nu, so you get the Laplacian here, and a del dot E here, so that you can just combine them together, and then divided by multiply d over 2, you get this, or is equal to 0, sorry. Okay. So this equation will restrict yourself transformation has to take the following form. It's called up to quadratic for general dimension. So this is So this is up quadratic in general dimension in X. Okay. So that's a huge difference in 2D and general dimension D. So in 2D here you have infinite. I mean it's just holomorphic function. So you can go to up to any polynomial degree, z to the some power, any power. But here it's only quadratic for general dimension D. And then people often write, so b mu nu, you just decompose the some almost trace part, and then m mu nu, antisymmetric part. Symmetric part, antisymmetric part, where it is mu is equal to minus m nu mu. So this is symmetric and antisymmetric part. And then also this C, question C, question C is often people write as follows: eta mu nu f rho plus eta mu rho f mu minus eta nu rho f mu, where f mu can be understood 1 over d c rho rho. Okay. So people often write like this way. So the reason why you would do is that the one can decompose the conformal transformation by generator transformation by generator. So one can find the generators. So for instance, if you look at the A mu, this is just constant. So x mu goes to x mu plus A mu. This is translation. This is translation. So, and generator is just P mu, which is just derivative, as you know. And unfortunately, I'm not careful about the coefficient. This is somehow the convention I use. And here alpha is just dilatation. It's just scaling transformation. So x mu goes to alpha x mu. Therefore, dilatation operator is x mu to the partial mu. So this is dilatation. And then again you have I here. And as you can easily see, so this antisymmetric second tensor is Lorentz symmetry. So this x mu is mapped to m mu nu x mu. So this is Lorentz transformation. Usually people just write down, I don't know why, I use different L mu nu. It's just, rotation in Minkowski signature. And then what is the corresponding F here? So this F here is the bit unfamiliar one, so it's called special component transformation. It's called special component transformation. So that map to indeed x mu is mapped to x mu minus x dot x f mu, as far as I remember, yeah, f mu, and a bunch of some particular denominator plus f dot f x dot x. So this is the so-called special component transformation. That is the infinitesimal version is actually it's somehow as we will see, this is somehow related to P mu. It's minus I to x mu x dot del x dot x. So this is the generator of special component transformation. Okay. Okay. So this is the generator of the special component transformation. And unfortunately, we need to choke. A generator of component transformation. And indeed, if you are very, very diligent enough, you can define the generator J mu. Sorry, JAB maybe. J mu nu is equal to L mu nu, and also J d plus 1 d. Okay, I think I should write like this. Sorry, I think it's not the clever way to write down. I think so. This is d, and then here you have 1/2 k mu minus p mu, and then you have the 1/2 k mu plus p mu, and then also you can have L mu. And then I think, am I making a mistake or not? I think I'm making a mistake. This is not the right way to write down. Sorry. So let me be precise. Okay. So you have d plus 1 and d plus 1 and d direction. And then here you have the 0 to d minus 1 dot 0. Okay. So this is the matrix we will consider. So here you have L mu nu. Okay. And then here also you can consider, here is, let's see, 1/2. So this is D. And here you just consider, here is you consider 1/2 K mu minus P mu. And also the same here. This should be anti-symmetric. So this should be anti-symmetric so that here you have a minus 1/2 K mu minus P mu. And you have a dilatation operator minus D. And here you have the 1/2 K mu plus P mu. And also you have minus 1/2 K mu plus P mu. And they have a 0, 0. Okay. So this is the matrix we will consider. Okay, good. So this is the matrix we consider. So this is called JAB. So including so K mu, P mu, and Dirac operator, in addition to this Lorentz symmetry, you can get the so of course this is element in SO 1, D minus 1. But now the size is the increase by 2. And indeed, this is the element of SO 2, D. So the algebra of this some generalized Lorentz symmetry is indeed, I mean, as you learn from QFT course, CD is equal to I Ada AB JBC plus Ada BC JAD minus Ada AC JBD minus Ada BD JSC. So this is the Lie algebra for SOD 2, D, where here Ada AB is minus 1, 1. So this is the 2, D. So 2, this direction is 2, and this direction is D. So if you look at the generator of this conformal symmetry, conformal transformation, and it combine in nice way, this becomes SO2, D. So this is the conformal symmetry of the general dimension. So in other words, if you have a conformal field theory, indeed, so usual quantum field theory enjoys the Lorentz symmetry. So QFT should be invariant under Lorentz symmetry SO1, D minus 1, usually. But however, for CFT in general dimension, so the symmetries get enhanced. SO2, D. So this is the Lorentz group, and this is the conformal group in general dimension. Okay. So indeed, so this special compound transformation is indeed related, is included the inversion. So if we consider this schematic diagram, just a unit circle, and then put so the point x mu, and then so the point x mu, so here you just consider inversion with respect to unit circle. So you just consider unit circle and bring it to the output. So therefore here is, I hope what I said is correct. Let me, I mean, it's recorded. Last time I told you huge mistake. So let me, I just written down correctly last time. Yeah. So what we do is at the following. So yeah. I think I should include this diagram in lecture note. The compound transformation, special compound transformation is indeed, you start with, I mean, with unit circle, and you just start with whatever x mu, okay? And take the inversion. So you just take the, here is, this point is x mu divided by x dot x, okay? X dot x, and then take the translation by f mu. F mu. And then again take the inversion of this point. This is x prime mu. Sorry, I think I should connect to the. So that's the global version of special compound transformation. So you start with point x mu and take inversion and do the translation, and again take inversion. Okay, so that's the global version of this special compound transformation. So yeah, but yeah, but here is infinitesimal version. Okay. Any questions so far? Okay, so including this special compound transformation, translation, dilatation, the symmetry of QFT is get enhanced to the compound symmetry. And in 2D CFT, we had a notion about the primary field. So do you remember the primary field? It behaves like OW such that the H divided by Z minus W square plus OW Z minus W. And then I think I missed something. Is it partial derivative? Do you remember? This is odd, and this is good. So this is how it behaves for the primary field. And then H is compound dimension. That's the behavior of primary field. So on the other hand, for general dimension, the primary field in general dimension is the defined by representation of compound group, indeed. Of course, it behaves like a K mu, and it's So, so the scaling transformation is generated by the dilatation. So, indeed, you have lambda x. So we have the lambda nabla. Oh, sorry. The delta. So today I talk about delta instead of h. I write phi of x. That's the scaling dimension or scaling dimension operator, and then from here one can just deduce how it behaves the primary field. So primary field is behaved as a representation of conformal group by under the Z generator. So primary field. Oh, I already write that. So when translation is acts on mu phi, so this is the usual property of the field, and also so D. So this one is important one. Phi acts on the scaling transformation like this way. Phi of x. And then, so from here, you can have a computational relation like this way. So P mu and K mu is indeed equal to I. So everything has to be compatible with computational relation of the conformal group. Is indeed. Oh, sorry. I think before then I have to include M mu. Plus delta mu and phi of x. This one is some representation of the Lorentz group. So this is the representation of the so if you have, I'm not gonna write down 2. Yeah, I think I should write down everything. So I x squared partial mu minus 2 x mu x dot del plus 2x plus 2x mu delta is of course scaling dimension, minus 2x mu lambda mu. Okay. This is how the conformal group acts on the field, and then if the if this K mu annihilates zero, this is annihilates 0, then this is phi is primary operator. Is primary. So this is how you define the primary field operator, primary field, with conformal dimension delta. So that's how you define the primary field of the general dimension. And in particular, so if you can, so in particular, so you can have the so if you have a primary operator phi, this is the primary, and you can just have descendant. So if you act on p mu or phi, this is a descendant. Lots of p to some power l. I mean p mu 1 p mu l is called descendant. So that's the definition of primary and descendant. I mean, yeah. So you have a how to say a higher state of coming from primary field in conformal field theory, and you can just act a bunch of the how to say Virasoro generator n1 dot l minus nk and l acts on h. Those are the same as descendant field by state operator correspondence. So the primary field corresponds to some higher state of the representation of Virasoro algebra, and you can act a bunch of the Virasoro generator so that you can define the descendant states or descendant operator. So it's very similar thing happening here. Okay, so that the K mu can be understood as the annihilation operator, and the P mu can be understood raising operator, or creation or annihilation operator. Yeah, whichever. Yeah. Okay. That's how you define the primary operator in general dimension. Oh, maybe I should mention, sorry. I didn't mention, so D acts on P mu is equal to minus IP mu. I mean, from this relation, and also D acts on K mu is plus IP mu. Sorry, K mu. And since D acts on diagonally on the operator, so this can be understood as some kind of Hamiltonian. Okay, Hamiltonian. And then P mu have a minus sign. This can be understood raising operator. If you define P mu as a raising operator, K mu has plus sign, so it becomes lowering operator. So that you can treat this as lowering operator, so that the primary field is annihilated by K. So that's another way to look. Yeah, that's the right way to look. And then, so yeah, so in dimension, D dimension, now CFT. So there is a unitarity one such that the dot conformal dimension has to be D minus 2 over 2 for scalar. And then, so delta has to be D minus 1 over 2 for skinars. In general, you have delta divided by 2. I think I made the typo is D plus S minus 2 over 2. I think I missed 2 here in the lecture note for spin S. Sorry. Where did I make a mistake? Let's see. Did I make a mistake or not? I think something wrong here. This one, I can't, I need to be careful. Ah. I wish, I mean, this should be true, right? Is it, this should be true, I would imagine. Okay, I think what I miss is, I think like this, I should write, my lecture note should be like this way. Okay, so this is the unitarity bound, it's unitarity bound. So this